Welcome back to Computer Science 305. This is a continuation of the talk on parameters. And now we've just got done. We talked about a little bit of the intro and the problems associated with parameters and parameter passing. And we got into parameter correspondence. And now we're going to be talking about implementation techniques for parameter passing. And so there's 7 different techniques that we're going to be referring to, and the first one is by value, and this one's probably the simplest approach. It's most widely used, and it's as the book calls it, the only method in real Java. I'm not so sure what real Java is, but regardless of that, basically what we're going to do is for by value. So we have the formal parameter is considered a local variable in the activation record of the called method. But with one minor difference. It's initialized using the value of the corresponding actual parameter. So we initialize this local variable given the whatever the evaluation of the actual parameter became, thus giving a prior to the called method executing. So it's pretty simple to understand, at least in my opinion. So for example, if we have some method plus that takes in 2 integers a and b, and it then takes the value of a and adds to that b and reassigns that value to a and returns a. When we call that in f with plus, and then we have the actual parameters xy, where x is 3 and y is 4. So that means we initialize a and in plus with the value of x, which is 3, and we initialize the b in plus with the value of y, which is 4. Then it comes out to be that it will be 3 plus equals 4, making a equal to 7, and returns 7 as the result, which is then stored to z in f. Pretty easy to understand, right? So the thing that we have to be concerned with whenever we're talking about parameters is what changes will actually be visible to the caller of the method. So when we pass by value, changes to any formal parameter have no effect on the actual parameter. So we see no changes to a point. And this only in Java, this only applies to primitive values, because if we pass in an object, although the changes to the actual parameter itself, for example, if we reassign the formal parameter, no change would happen to the actual parameter. On the other hand, if we make adjustments to the object referred to by the formal parameter and the actual parameter, we would then see that change on the caller side. So bear that in mind. The value of the parameter, and that gets into this third point where we're talking about the value of the parameter could be an actual pointer or reference in Java. We cannot change the actual parameter, but the object referred to by the actual parameter can be, as I just said. So, for example, in this case, we have some function f that has creates a new con cell, right? If we recall from the cons list in Java, and we initialize it with a value of 0, and it points to another the pointer from this con cell to the next is null. We then call the method alter. Alter then takes in value 3, and which is assigned to new head, and then the value x with the con cell x, which is then passed as the initialization value for the con cell c. So in essence, what we're going to be seeing is what's going on over here. Both c and x point to the same object on the heap. The void alter method then sets the head of c, right, to be new head, so 3, and then it assigns to c the null pointer. So what ends up happening is, as we can see here, we make that change. The head value for the con cell that both x and c were pointing to is now 3, and then we made c null, but that doesn't change what x is, right? So there's no actual thing going on here. No actual changes on the caller side of this, only on when we actually do the reassignment, which makes complete sense. And I would say this is the reason why they make the claim that although we are passing by reference, technically, we are not referring to the formal parameter never refers to the actual parameter. Rather, they just refer to the same object in memory. So by result, this is the next method, right? Essentially, this is what we will call a copy out parameter. So by value was a copy in parameter. Here we define a variable that's an out parameter for our formal parameter in our parameter list. Essentially, no value gets applied here. Rather, what happens is there's a what we give it is an L value, so a memory location in which we're going to store a value after the method is finished executing. This is originally introduced back in Algol 68, and it was sometimes used in Ada, but in reality, almost nowhere uses this. What we do have, so if we were to create this and we have some fictionalized by result keyword up here in the plus method, which is just indicating that the type of parameter is a by result parameter. So if we had this, essentially, when we make this call in F, right, we have three values, X, Y, and Z. Z is not initialized. Z is going to be the storage location for the by result from the plus method. So we copy in the value for X into A, so that'd be 3. The value for Y into B in plus, and that would be 4. And then C is unknown, right, because that's going to be our holder for our value. So what's going to happen is we're going to add A and B together. That'll give us the value of 7, and we're going to store that to the location for C. And that will actually be the same as the memory location for Z. So if we were to do this, when plus is about ready to return, right now we've updated the value of C is now 7, and then when it does finally return, right, Z now stores the same value that C had, which is 7, right? So that value gets copied out and back to the provided actual parameter, right? So if we ask ourselves, what are the changes that we can see on the caller side? Well, we obviously can see the change to the third, or the by result parameter, actual parameter, is changed by the called method. There's also another approach, which is value result, which is a combination of the two. The two previous approaches, and basically, so what we can do is we have some formal parameter defined as a value result parameter. Not only will you be able to initialize it with an existing value, so that it can be used inside the method, but then whatever the changed value that it has will be copied back out to and then stored in the same memory location. So essentially, it's just a versatile approach that we will see the changes on the other side. So it must be an L value, so in other words, a place that can be assigned to, but at the same time also can have an existing value prior. So if we have the same plus, now this time we have only two values. One is the integer A, which is a by value, and then we have the by value result B, which we're going to do a plus equals to. So we're going to use the value of B, add it to the value of A, and then reassign it to B. So when we call F, right, we have we create an integer X that's equal to 3. So that gives us an L value, right? X is a variable that we can assign to, but it also has the value 3. So when we call plus, we copy in the value 4 into A, and then the location X into B. So this then gives B a value of 3 and A a value of 4. And so when we get ready to return, right, right before plus returns, B is now a value of 7. X is still 3 in the calling method. And then finally, when plus returns, it updates the value of X to be 7, the same value as B. So pretty easy to understand how this works. There could be some issues with that, but not that big of a deal right now. By reference, on the other hand, is a little bit more interesting. So passing parameters by reference, right? We give the L value, the actual location in memory, the address. The actual parameter is computed prior to the called method executes. And then inside the called method, this L value is used as the L value for the corresponding formal parameter. So in effect, the parameter becomes an alias for the actual parameter, right? The formal parameter is an alias to the actual parameter, which means that they have the same memory location. It's one of the original earliest methods that is used back in Fortran, and it's very efficient for when we have really large objects in memory. And it's still widely used in other languages. So if we think about this, right, if we have the same plus, now we have A and by reference int B. Same thing as before, we're going plus equals A to B. And then what we do is when we make this call to plus from F, we're going to pass in the memory location of X. X is currently storing 3 at that memory location, and then we copy in by value the value 4 for A in plus. And so essentially, as we can see here, when plus starts, right, A is 4, and now B is pointing directly to X, right? So they are the same memory location. So when we actually execute this, B sees 3, and then A is 4, and so that will, when we call the plus equals, that will store 7 at B, but he immediately updates X. So as we note that we made that change because B and X are aliased, and therefore prior to plus even returning, this is right after the assignment was made, then X is already updated as 7. So that one's pretty easy to see, and we can actually utilize this, for example, in C languages where we have pointers. We can pass in the address of, right? So as we can see here, we have the pointer B. We say star B plus equals A, right? And then that will, and then we pass into B the address value at X, right? Which gives us a by reference approach. Aliasing, as we should know, is that we have two expressions, the same L value. They are aliased to each other. If we think of in Java, everything, whenever we assign one variable to be equal to another variable, that is aliasing, except for in the case of primitives, right? This only is for objects, which then includes messing with, we'll say the use of array objects, right? So if we say one array cell is equal to 2 different array cells, that is another type of aliasing. Anyway, so we pass by reference can lead to some less obvious cases that are possibly dangerous. So if we think about this, we have the method SIGSUM, right, which takes in by reference 2 different values, n and ands. So the answer ans is equal to 0 initially, then we have some integer I equal to 1, and while I is less than or equal to n, ans plus equals I plus plus, right? So it's just updating ans until to be the value of n effectively whenever the while loop is finished. Now, the problem here is, if we run this as with the F method, it works just fine, right? So we copy in the address of x and y for n and ans, where x initially points to 10. We call a SIGSUM, and then we're going to return the value of y. So if we do this, it's no big deal. Y has no associated value yet. When we pass this in, we pass in 10. So ans equals, we then assign to y from f, right, 10. 0. And then we walk from I equals 1 until we reach 10. And we update ans by 1 each time, by I each time. So this would be whatever the summation of each individual item in from 1 to 10 is. I'm not going to do that math in my head. But anyway, that would be the return value of y. Now, on the other hand, if we run this with g, and I'll move this to the next slide. So when we do this with g, right, this leads us to a different problem. As I alluded to in class on Friday, it is a and had you guys figure out is basically this turns out to be 0, and the reason for that is if we just have one variable x, we point it at 10, and it's the what both n and a and s in SIGSUM point to. What will happen is, and it will initially assign straight up a and s equals 0, which then makes n equal to 0, right? Because n and a and s are both alias to x. The second we change a and s, we change x. N now points to x. X is 0, and therefore n is 0. So int I will be 1, but I will be greater than 0. Therefore, the while loop will never move forward, and thus the return value of g will be 0, right? The value of x. So as we can, so that's one of the dangers of using this is you have to, if you are going to be using these different approaches, you have to really understand what's going on when you use them. All right, that's the whole point of this entire lecture is knowing what, looking at whatever your language is, knowing how its underlying components work is a very key thing to being able to program effectively in that language. Next approach is by macro expansion. This is an interesting approach. It's been used since way back in the old days of assembly language as well as C. Basically what it's going to do is there's macros that we can define that whenever we utilize that macro in code, prior to compilation, it will be that exact code will be copied directly in, and then and then we'll utilize the context of wherever it's at in that to fill in the details. So we'll kind of look at that in a second here. It's basically just text substitution. So let's think about this, right? We have some editor and a source file. We define some macro. For example, here we defined min takes in xy. So it looks like a function, but it's not. And then what that's going to do is for whatever xy we put in, we're going to replace x and y with the actual parameters. In this case, in the file, it would be bc. So we see it would be b is less than c. If that's true, then b, else c. But this is handled by a preprocessor, so it will be copied in prior to the compiling actually occurring. So we'll see the expanded source that we get here at the point in time prior to right before compilation occurs. Now we have to understand that the preprocessing step will replace each use of that macro with a copy of the macro's body with the actual substitute for the formal parameters of the macro. So it's a very old technique, as I said before. It's used by in assembly language, but it has some really odd effects. Specifically, each actual parameter will be reevaluated every time it's used. So this is dangerous if you use things that have if your parameters have side effects. So side effect type parameter would be if it's an expression that you're using, which updates a value. For example, B++, C++, right? That's incremental assignment. So we're changing the value of B and then changing the value of C. So initially, because this is a post increment, what will happen is the first time we see B or C, we will see that value. So we see when this is actually evaluated, it will be B is less than C, or it'd be B plus 1, which then will be the value that we see for A, or C plus 1, the value for A, and then B and C will again be updated. So this is a nasty experience for understanding what this is actually going to do, and can be very dangerous very quickly and give you very weird errors or wrong values that that can be difficult to track down. Furthermore, there's this problem of capture. So if we think about this, right, we have the second example here. We defined int swap, which takes in x, y, and then the piece of code that it injects would be that we're assigning to temp, some variable temp, which is a variable defined as a part of the macro, the formal parameter x. Then we're going to swap x with y and then y with temp. Well, that's all good unless we defined a temp in our actual code where we're going to be using this, right? What will end up happening is that will cause a capture, and so if we see this expanded, capture is basically where if we have some variable defined in the macro that's also being utilized in the context where the macro is going to be expanded at, that will cause that macro variable to be captured and hold the value of whatever variable was there in the context in which it's expanded to. So as we can see down below, that essentially gives us we create a temp equals 1, b equals 2. The problem here is we create a new scope with the curly brace, and so that new scope will say that temp equals temp. It doesn't know what that means. I don't know what that means because temp was just created, so we have no value for that. Furthermore, temp equals b and b equals temp. So all this is not making any sense when we look at this code, and it will end up causing compilation error most likely. Basically, capture, as I said before, so if we have a program fragment, right, any occurrence of a variable that's not statically bound is what we'll call free. And so when a fragment is moved to a different context, its free variables can become bound, as we saw before. We're binding in temp, right? And now leading us to a problem with this capture, right? So free variables in the actuals, right, the actual parameters can be captured by definitions in the macro body, and those free variables in the macro body can then be captured by, or those free variables in the macro body could be captured by definitions in the caller. So all this is leads to several issues that can possibly occur. Although sometimes that is what you want, right? If you design this correctly, you can actually have it so that that works to your advantage. The next type of parameter passing technique is called by name. And so when we're passing parameters by name, each actual parameter is evaluated in the caller's context on every use of the corresponding formal parameter. So basically, it's similar to macro expansion, but it doesn't allow for the capture to occur. It's not really used by, I don't know of any languages that are in current use that actually have this, but it can be done by and the way it's typically done is by creating the taking the actual parameter and treating it like it's an anonymous function. So whenever the called method needs the value of the formal parameter, either the R value or L value, it calls the function to get it, right? So the function must be passed with its nesting links that can be evaluated in the caller's context. So essentially what we see here is we have a function f, right, that takes in by name A and by name B, which then it assigns to B the value of 5 and assigns to B again the value of A. So essentially what's going to happen here is that we have G, and we say I equals 3, and then we provide a values to the function f, I plus 1 and I. So essentially what happens is when we provide the value for A, right, that's going to point to a new function which calculates I plus 1. And then if we have B, that's going to give us a new function I, right? So interestingly enough, these are both by value and they are both acting as almost like a reference, right? So what happens is when I assign B equals 5, that's going to assign the value of 5 basically to I. I will update to be 5. When we call A, right, it'll be A equals A will be I plus 1, so it's going to contact that anonymous function to get the value of I plus 1. that will look for I, go back to its point back to the nesting link through to get to the value of I. I is 5, and it'll be 5 plus 1, which would be 6. So now B is 6. That will update I again. I is 6 at the end. So if we want to think about this, right? The way this works is just like in macro expansion, by name parameters are reevaluated every time they are used. So that's how all those changes occurred. It's typically this can actually, if you know how to use this technique, it becomes very useful. But all these reevaluations tend to make it exceptionally wasteful because you're constantly recalculating things. But we also know that because it's using these anonymous functions style of approach, we have no possibility for capture, right? Because they're off away from the actual definition of where they came from, and thus we don't have to worry about any variables becoming captured as we do in macro expansion. Macro expansion literally copies text into the code, or uses text substitution in the code, and then thus provides the capability for capture, which can be dangerous. One of the last ones by need. So this is an interesting. So what we do is we pass in parameters by need. So each actual parameter is evaluated in the caller's context, right? So where the caller is on the first use of that corresponding formal parameter. So unless we actually need the value, we don't do the evaluation. Only when it's needed. The value of the actual parameter is then cached, right? So we can, so then it's stored, and then anytime we need to update that, anytime we need to get the value again, we don't have to go and recalculate it back in the formal, back in the actual caller's context. We just have that value ready to go at any one time, right? And this is basically called lazy evaluation, right? We don't do the evaluation unless we need to, and once we've done it, we don't do it again. And this is utilized in the functional language Haskell. And this, of course, avoids the wasteful recomputations that were found in the by name approach that we saw just previously. So it's very similar, right? We have the same anonymous function type thing going on, but this time we're going to say by need into A and by need in B for F, and then we're going to do the assignment of A to B twice. And so what will happen is if we run this, we see that G, just like before, has the value of I equals 3, and then we're going to pass in I plus 1 and I plus 1 for A and I for B. So what will happen here is, right, on the first use in F, we'll have B equals A. So A equals I plus 1, so it will calculate that. Goes in the I plus 1 on this function, since this is the first time we've needed it. We'll then go in and look up I plus 1, which would be 3 plus 1 is 4. So it then knows that A is equal to 4, right? Now, the interesting thing is B is I. So we assign 4 to B. B gives that to I, so now I is 4. So if we do on the second approach, right, we say B equals A. Well, we're not in this. We're not going to go and recalculate A. We already know A is equal to 4. We don't have to go. If this was by name, then it would go and recalculate A, and A would be I plus 1 would be 4 plus 1 would be 5, and then B would assign 5 to I. In reality, because this is by need, it will not do that, and it just reassigns to B 4. So because we cached the value of A after that initial evaluation, right? So in essence, although we have these links there, it only does it one time as needed, right? And then it's as if we have that value associated with this specific implementation of or this specific activation record. And so by the time it gets done, when we return at G, we return I is going to be equal to 4. Furthermore, the laziness, right? We can also think about this if we think about the short-circuiting of and also in Java's double and operator. If we wanted to create our own Boolean using by need, we have an and function, right, which takes in a Boolean A and a Boolean B on the by need. And so then it says, if not A, return false, else return B. Now we pass in we have G, which then has a while true loop, which is an infinite loop, and then it has a return true, but which will never it will never get to. Finally, the actual calling method F, which calls and passes in false, right, and then a call to G. So what will happen is we have an anonymous function that calls G, and we have an anonymous function that returns just false straight up. So when we get back up to and, it's going to look at that. It's going to say, first thing I need to do is say not A. So we're going to check that. And it's going to say have it evaluate A, and that will return false. That returns false. So not false is true. So it hits that and then immediately returns false. It never evaluates B, right? And then it moves on. So the return value for and will be false. Thus, we never hit the infinite loop inside of G. So that ends this section, and the next thing we'll talk about is specification issues.